All right, so finishing up, we've got a few more examples on derivatives as a rate of change. So now these are very similar to web work homework problems you guys are going to have. So here our setup is a particle moves along a coordinate axis in the positive direction to the right. Its position at time t is given by blah. We're going to find the velocity at 1 and the acceleration at 1, and then we're going to answer questions. So let's just start finding our functions. So I'm just going to recopy our function down. So we have t cubed minus 4t plus 2. So this won't be too bad. So our velocity function first, which is the first derivative of the position function. So t cubed, derivative of that using our power rule, bring the power down, 3 times t, and then instead of the third power, it's now 1 less, so we have 3t squared. Minus 4 times the derivative of t. That is t to the first power, so we have 1 t to the 0. Plus, the derivative of a constant is 0. So our velocity function is 3t squared minus 4. Right now, our acceleration function, that is the derivative of the velocity function, which is the second derivative of the position function. So just taking the derivative of that result we just had, so I have 3 times the derivative of t squared, the 2 comes down, t to the 2 minus 1 is 1, minus 4 is now just a constant, so the derivative of a constant is just 0. Sorry, normally it's like a t squared and then a t term, so I was expecting it to be a constant. I was like, yeah. So our acceleration function is just 6t. Now they asked us to figure out v of a, v of 1, and a of 1. So v of 1 will be 3 times 1 squared minus 4. 3 minus 4 will be negative 1. And then a of 1 is just 6 times 1, so we get positive 6. So, is the particle moving from left to right or from right to left at time t equals 1? So at t equals 1, our velocity is negative. They said the positive direction is to the right. So if our velocity was positive, it would be moving towards the right. Since it is negative, this is moving to the left. So from right to left. Is the particle speeding up or slowing down? So the velocity is negative. It's pointing this particle towards the left. The acceleration is positive 6. So since these are different signs, one is negative and one is positive, they're acting opposite poles from each other. So this is going to slow down. So that's how we can answer the question about, is it speeding up or slowing down at a value? We find what the velocity is at that value. We find the acceleration at that value. We compare whether they're in the same direction or opposite directions. Now we're going to do that same thing, but we're going to do it for the entire function. We're going to figure out everywhere this crazy particle is speeding up and slowing down. Now, this has been a favorite question on tests in the past. It is kind of complicated and kind of involved, though, And it's a bit of a pain to write a function that's not too complicated for the working out. But let's practice what we got here. Now, they did provide us a little bonus caveat. We only care about the values from 0 to 4. So suppose a particle moves along a horizontal coordinate line in such a way that its position is described by the function blah for 0 less than t less than 4. Find the particle's velocity as a function of time. Determine the open intervals on which the particle is moving to the right or to the left. Now, in this case, to the right is positive, to the left is negative. So this is really asking us to find a sign chart, or I like to use a number line to really organize this information, because we're actually going to stack the information from this question with the next question. It's all with the same function. But first things first is our position function. So we have 4t cubed minus 26t squared plus 51t plus 4. We're going to take the derivative. That's not that bad. That's a whole lot of power rule. We can do this. 4 times the derivative of t cubed, we bring the power down, 3t squared, minus 26 times the derivative of t squared, we bring the power down, 2 times t to the first power, plus we have 51, that is t to the first, so that is 51 times 1 t to the 0. Now, after a while, when you've written that 1 t to the 0 enough, you start to realize that's times 1. And, well, you don't have to write times 1 because it's just the number. So once you do enough derivatives, you're going to start to get real familiar with the rules, and you'll be able to start skipping showing as much work. Like here, the derivative of a constant is 0. Well, adding 0 doesn't change anything. So after a while, you'll stop writing the plus 0. But eventually, like towards the end of Cal 1, and really the focus of Cal 2, is how to do this process backwards. So eventually you're going to get to the point where you're very fluid at this. You don't have to think about the steps. And then we're going to say, hold on, now do it all backwards. And now you have to remember all the steps that you stopped writing. So, like, get to the point where you can stop writing them, but don't completely forget about them, because you're going to want them back. So our velocity function, that is 12t squared minus 52t plus 51. And we want to figure out where is it moving right and where is it moving left. So to determine where it's moving right and left, the easiest thing to do would be to figure out when it's not moving right or left, when the velocity is 0. So we are going to take this function and set it equal to 0, which now means it is a quadratic function. Now that might factor, but I really don't want to play around with the pairs of numbers that 12 times 51 is going to be to try to see if 52 is in there when odds are actually kind of high it won't factor. Now on the test, these numbers are a little too big and ugly. So if we put one like this on the test, I would imagine the numbers would be smaller, but I would not necessarily expect them to be pretty. I would still expect you to have to pull out the quadratic formula for this. So t equals, because that's our variable, negative, b is negative, so we have negative 52, plus or minus the square root of b squared is negative 52 squared, minus 4 times 12 times 51, all over 2a. A is 12. All right, so handy dandy calculator time. I got no clue what 52 squared is. I don't want to know, except I'm about to know because I'm typing it in the calculator. 52 squared is apparently 2,704. Now we're going to minus 4 times 12 times 51. Hey, 256, that's actually a nice number. So my t is 52 plus or minus square root of 256 all over 24. So 256 raised to the 0.5 power is the square root. 256 is 16 squared. So I have 52 plus or minus 16 all over 24. So I'm going to split that 2 ways. The 52 plus 16 is 68 over 24. Which is not a pretty number. And then 52 minus 16 is 36. So 36 divided by 24 is at least decently nice. That's 1.5. The 68 over 24 is, looks like 2 5/6. This is 2.833, where the 3's go on. I'm pretty sure that's 5/6. But 68 is divisible by 4. 24 is divisible by 4. So we'd get 6ths. So these two numbers, though, are between 0 and 4. So these are the spots where the velocity is 0. So I'm going to draw a nice number line now. So the start of my number line is going to be 0. The end of the number line is going to be 4. And then in between, I'm going to have those two values I just found, the 1.5 and the 2.83 repeating. So our function is, since it was a t cubed function, like it was a ridiculous 4t cubed, but it's still starting from negative infinity. It goes up, turns around, goes down for a while, turns around, and then goes back up. That's how we expect the normal function to work. We're going to translate this, though, into going up is going right. So it goes right, then it turns around and goes left for a while, then it turns around and goes right for a while. But since we're not like seeing that's how the function moves, how it's supposed to work here, may not be that obvious to you. So the other thing we can do is we're going to plug in test values into our function here. So I'm going to pick, now in this case, 1.5 and the 2.83, those are 0 for the velocity. Let's label this is v of t. But if I plug in 0 into my velocity function, I'm going to get 51. So everything from negative infinity to 1.5 is the same sign as that 51 we just got. So everything in here is positive. So I like to put a whole bunch of little plus signs in there just to show myself positive velocity in all of these sets. All right, now in between 1.5 and 2.83, I want to pick a test number. I'm going to pick 2 as a test number. Now, if I substitute 2 into that function, that actually takes some number crunching. So let's number crunch. 12 times 2 squared minus 52 times 2 plus 51 is -5. So since 2 has a velocity of -5, all of the numbers in that interval from 1.5 to 2.83 are going to be negative. And that's because we figured out the zeros, so it can't change to positive anywhere in that interval, or there would be another 0. So as long as you're confident in your ability to find where the velocity was 0, then you can confidently use a test value to determine whether that whole interval was positive or negative. Now, most functions are just going to alternate, so it's not surprising that it's positive, then negative, and we're probably going to see positive for this third region, but that's not always guaranteed. Sometimes it'll be decreasing, it'll flatten out, and then it'll keep decreasing. So I would still recommend like testing it for every interval. So I'm going back in and I'm changing my 2 squared and my times 2 to 4 squared and times 4. And so over here, I'm getting a value of 35, positive 35. So everything here is positive, even past the 4. So let me just write that to the side to be a little more explicit about what I just did. So I figured out that the velocity of 0 was 51. Figured out that the velocity at 2 was -5. And I figured out that the velocity of 4 was positive 35. So that 4 is some number to the right of 2.83. And since it was positive, everything to the right of 2.83 is going to have positive velocity. So that's what our test values were for. We were just seeing, is it positive or negative? The fact that we got actual numbers is kind of a whatever. So the question was, when is it moving to the right? When is it moving to the left? So we would say that we are moving right when it's positive. So right. So I'm going to write positive in parentheses. That is from 0 to 1.5. And it's from the 2.83 repeating to 4. Now, WebWork may not like 2.83 repeating, so you could also write just the 68 over 24 there instead when you're typing your answer in, because WebWork does prefer precision the most. Now, they said the open intervals. So what I am not sure is if they want open parentheses everywhere. So I know for sure the 1.5 and the 2.83, those are open parentheses. The 0 and the 4, though, technically at 0, the particle is moving to the right. So we could include 0 in that interval, but the directions said determine the open intervals on which the particle is moving to the right and to the left. So I don't know if they actually want us to put open parentheses or a bracket there. I would just try both and see what WebWork takes. But like from the technical side of things, like at 0, it is going right. And at 4, it is also going right. So like me personally, I would put the brackets because that is included. But the direction said open, so they may want it open. If they don't like the 2.83333, you should be able to type the 68 over 24. It may want you to reduce it, in which case, like I said, those are both divisible by 4. So let's see, 68 divided by 4 is 17. So that would be 17/6. So if WebWork is persnickety about decimals, go with the reduced fraction. Or sometimes WebWork will even take the unreduced fraction. Now, the other thing to note here is I didn't write a symbol in between these open intervals. That is because in pre-cal, when y'all had to do this, you would put a U in between the open intervals. In calculus, though, for some reason, almost all of the WebWork questions don't want the U, they want a comma. And I find this annoying because you already have commas in the middle of the open intervals, so then putting a comma in between 2 parentheses, it's really easy to not be able to see the comma there. So like pay careful attention to what you're typing and kind of have faith that what you typed is what there, even if you can't see it. But if you type in the union symbol, like if you go searching for it on the side keyboard and press it, or if you type in a capital U, like don't be surprised if WebWork is like, I don't like that. So there is our, where is it moving right? Now we've also got to answer where is it moving left? And that's going to be the negative region, which is the other part, the in-between. So that is from 1.5 to the 2.83 repeating, or probably you could just use the 17/6. But to understand where 17/6 was, we needed the decimal. So we did need to know the 2.83 just to know how big it was. That way I knew 2 was in between those two numbers. 17/6, though, it's not as obvious. Like, how big is that? Oh, I got to think. All right, so we used interval notation there. So all of those are X numbers. There are no Y numbers there. Now we're going to do that whole same process for the acceleration, and then we're going to combine the information together to answer about speeding up and slowing down. So same function, 4t cubed minus 26t squared plus 51t plus 4. Now let me rewrite the velocity function. That is 12t squared minus 52t plus 51. Now we are going to come up with the acceleration function. Remember, acceleration is just the derivative of the velocity or the second derivative of the original function. So now it'll be 12 times the t squared. We bring the power down, 2 times t to the first, minus 52. And then t to the first here becomes 1t to the 0. And then the 51 is a constant, so it will just be plus nothing. So our acceleration function is 24t minus 52. Now, just like we did with the velocity function, I need to know when is the acceleration positive, when is the acceleration negative. That way I can compare it against the velocity to determine when it's speeding up and slowing down. So this isn't as simple as positive acceleration is speeding up, negative acceleration is slowing down. That is not always the case. It is highly dependent. It is required that you compare it with the velocity. When are they in the same direction? When are they in opposite directions? So to figure out the turning point for acceleration, we're going to set it equal to 0. Now, it's not a particularly nice number, but at least we're not having to use the quadratic formula. Add 52 over, so I have 52 equals 24t. Then I divide by the 24. All right, and that is at least divisible by 4 and only by 4. 52 cards in a deck of cards, 13 cards in a suit, and there's 4 suits, so 52 is 4 times 13. It's the only reason I remember that fact. So this reduced is 13/6, which is a little bit bigger than 2. This is going to be 2.16 repeating. So when we draw our number line, now remember, we have the boundary points from the original problem of 0 and 4. We don't actually care what happens before 0. We don't care what happens after 4. But our acceleration turns around. It is 0 at the 2.16 repeating, or the 13/6. So now I need to know, well, where is it negative? Where is it positive? Like, which side does what? So if I plug 0 into my acceleration, I'm going to work that up here. So the acceleration at 0 is 24 times 0 minus 52. So it'll be negative 52. So everything before 2.16 is negative acceleration. Now our acceleration at 4, 24 times 4, and then minus 52. 24 times 4 is bigger than 52, so this is positive. I don't actually care what the number is. I just care that I can tell it's a positive number. So now I know when the acceleration is negative, when the acceleration is positive. So now I am going to screenshot. So I circled all of that. No, it didn't circle all of it. There, I circled all of that. I'm going to Control C, Control V, and then I'm going to come back up here. All right, so number line for one was way bigger than my number line for the other one. All right, now let's zoom in here. Let me go ahead and label this one as A of t. So I'm now going to make a final number line where I can answer where the speed up and slowdown is. Now my final number line has to have all of those zeroed values and the endpoint values. So I'm actually going to make that number line a little bigger because y'all know my handwriting's big. So we got 0. Our next critical number is 1.5. Then we have that 2.16 repeating, which I'll write the 13/6 because I'm pretty sure we need the fractions in WebWork. Then we have the 2.83, which is the 17/6. And then we finally have 4. So I have 4 regions where I have to determine if it's speeding up or slowing down based on my graph up here. So notice that I've got them like almost lined up. So I'm going to kind of sketch that 1.5 here would go about there. And that 2.83 would go about there. So I can see in my first region from 0 to 1.5, my velocity is positive, my acceleration is negative. So velocity positive, acceleration negative. Those are different directions. So this is a slowdown region. Then our next region, I'm also going to take this 2.16 and we can kind of put it on top of the 2. It's close enough. So from 1.5 to 2.16, the velocity up there is negative. The acceleration is negative. So here they're matching. They're in the same direction. So now this is a speed up. So the velocity was originally positive, and a negative acceleration was dragging it backwards. So this particle was like doodling along like, I'm happy, going where I'm going. Why am I getting slowed down? Why is everything so slow? And eventually it stops, and this thing is still pulling on it. So it's like, okay, I guess we're going this way. We're really going this way. And then the acceleration was like, whoa, 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 hold on. I didn't want that much. Like less acceleration, negative, negative, and then boop, the acceleration changed. It went 0 at the 2.16, and now the acceleration is going positive. It's saying, oh, let's push, push. No, no, no. But our particle already got yanked that way, so it's still going that way, even though the acceleration changed direction. So now we've got to slow down again. Eventually, the new acceleration, the positive acceleration, slows it down to where the particle stops. And now it says, okay, okay, we're going this way now. And then the acceleration keeps pushing it. So from the 2.83, where my velocity and acceleration are both positive, now it's finally speeding up. So when we go to answer the question, to label these intervals, so slow down is from 0 to 1.5. And if that wasn't a terminal decimal, we'd want to use the fraction, but 1.5 is 3/2. Either will work. So that's our first slowing down interval. And then our next one is the 13/6 to 17/6. That's the other spot where it's slowing down. All right, now our speed up intervals. So from 1.5 to the 13/6, we're speeding up. And then from the 17/6 up until the 4, we're speeding up. Now don't forget, it's commas in between those intervals, or the proper mathematical notation would actually be the union symbol. So on the test, you could write it either way. Now, my only hesitation with this question, it's a very good question. You have to understand your derivatives, your power rule, the constant multiple rule, but you also have to showcase your algebra skills for using the quadratic formula and then setting a linear function equal to 0 and then combining all that information together. There's a whole lot going on in this problem. It's a great problem, but it's honestly a little too long for a test. Now, if we had a more basic function, like maybe the position function was a parabola, then it might be easier. Like then the first derivative would be linear, so you wouldn't have to do the quadratic stuff. And then the acceleration, the derivative of that, the second derivative of a quadratic is actually a constant. So then the acceleration is just one sign everywhere. And then you're only going to have one region where it's slowing down and one region where it's speeding up. Or it might be speeding up and then slowing down just based on what was going on. So this is me just like thinking about the future. I don't know what's on the test yet, but like in the past, this is absolutely a favorite of teachers because it tests so many concepts at once. It's a very rich, dense question. Very weird question. You really got to think about what is going on here and what that means. And then there's just our summary slide of everything that we were just talking about. All right, so we'll stop this here. And then the next video will be trig derivatives. Ooh.